Let's discuss the reactions of acid chlorides. There's only one way that we've learned to make an acid chloride, and that is from the corresponding carboxylic acid. Using SOCl2, we can make the acid chloride instead of the carboxylic acid. We make SO2 as a byproduct, and we make HCl. And so sometimes you might see pyridine written under here. That's to soak up this HCl that's produced. If you don't see pyridine, it should still work. We sometimes are a little bit lazy in terms of, do we add the sacrificial base or not? So this is really the only reaction that we know to make an acid chloride. If you can get to a carboxylic acid with any R group, you can make the corresponding acid chloride. The mechanism is in the book. I don't really feel a need to reproduce that for you here, but you should study that mechanism and know it. And so once we have the acid chloride, we can react that with a range of nucleophiles to produce a number of new functional groups. One really exciting reaction is to react the acid chloride with H2O to reform the carboxylic acid. So that's not that useful, but we might be supplied with a carboxylic acid chloride and want to turn it into a carboxylic acid, but generally this isn't going to be all that useful. Let's look at the mechanism of water reacting with an acid chloride. And as we've shown in the nucleophilic acyl substitution mechanism, the first step is attack by the nucleophile on the carbonyl carbon. And you'll see in this case, we've got that two charges present in our molecule. Remember we talked about that? We have a very reactive electrophile and a not so reactive nucleophile. In this case, it's okay to have these two charges because we have this really reactive electrophile. The next step then is to reform the carbonyl. We're going to lose a leaving group. We've got a couple options. The R is the worst option. That would result in a carbon anion being formed. We could kick out the nucleophile we just added, and indeed that probably happens often. It's just that we won't show that in a mechanism because it just wastes our time, because we'd get back to the starting material. So we probably do lose the nucleophile quite a bit, but the productive leaving group to lose would be the chloride. So let's show that leaving with another arrow here. I've reformed the carbonyl. I've added water. It still has a extra plus charge, and I've formed chloride. And in this case, I could use water probably to remove the extra hydrogen in a proton transfer step, and that brings me to the product. And so you can say that we produce HCl or H3O+, which is water that's in the presence of HCl. It gets protonated. And I would like to make a note here that often use pyridine. And pyridine is the aromatic compound with a basic nitrogen to soak up the HCl that's formed. And so that lone pair is basic. We call it a sacrificial base. We just add it to collect the HCl that's formed so that it doesn't have the opportunity to react with anything else on our molecule. For instance, something on the R group that we haven't specified here might be susceptible to acid. And we can also react acid chlorides with alcohols in the same manner as we saw with water. I'll put pyridine down below there, and it's the same mechanism as with water, so I'm not going to go through that. Final proton transfer step gives us the ester and HCl, and again HCl reacts with the pyridine. And so this is a way to make esters. So we've found a way to take acid chlorides back to the carboxylic acid. Generally that's not very productive because, as we've shown at the beginning of this video, we start from acid chlorides to make carboxylic acid. We start from carboxylic acids to make acid chlorides. However, it is very productive to take an acid chloride to an ester using an alcohol. We could also use the acid chloride and react that with a form of an amine. We could do NH3, and here we would just put in twice as much NH3 as we need because the ammonia can act as its own sacrificial base. So we'd make one equivalent of ammonium chloride with the extra NH3 plus the HCl that's produced. Here's where we soak up that HCl with the extra nitrogen base, as opposed to adding pyridine. And we could use, let's say, R groups here. We don't have to just use ammonia. We could use RNH2 to put one R group on our newly formed amide, and I could use 2 R's on my amine and put 2 R's on the newly formed amide in place of the 2 hydrogens. So I could use ammonia, primary amines, or secondary amines here to do my amide formation. And so this is amide, this is ester, and these are probably the 2 most common reactions that we will do with acid chlorides. Let's create the ester equivalent, or let's create the amide equivalent here. Let's look at the steric effects of this reaction. What if we had a molecule that looked like this with 2 different types of alcohols, and we reacted that with an acid chloride, some pyridine. Let's make sure that it's one equivalent of the acid chloride, and as you might expect, the secondary alcohol is less reactive because of sterics than the primary alcohol, and so we should be able to acylate the primary alcohol much more quickly, more rapidly than the secondary alcohol. And so the steric effects here, typically the more hindered alcohol will be less reactive. We might also consider starting with acid chlorides and reducing them, or reacting them with a Grignard of some sort. And these will work, but generally, because the acid chloride is so highly reactive, reducing it with LAH or even sodium borohydride is sometimes not such a good idea. And same with reacting with a Grignard. So if we want to do these, it's generally just better to start with the ester. Start with the ester equivalent. As we saw in our laboratory Grignard reaction, esters react with Grignards with no problem. So there's really no reason to take the ester and make it more reactive by turning it into an acid chloride. So we typically don't reduce acid chlorides, and we don't react them with Grignards. There is an exception to the reduction of acid chlorides being inadvisable, and that is where we use a special hydride reducing agent that looks like this. You can see we've replaced 3 of the hydrides on lithium aluminum hydride with alkoxides, and so we're tempering the reactivity of lithium aluminum hydride. We'll follow this up with mild acid workup, or sometimes just water. I prefer to write H3O+, but your text might just show water here. And this allows us to add just a single hydride and allows us to produce an aldehyde. So now we have a route to go from the carboxylic acid, which allows us to make a carboxylic acid chloride, which we can then use this moderated hydride reagent to add a single hydride to make an aldehyde. So this reduction of acid chlorides is actually very synthetically useful. It allows us to produce aldehydes in a way that we haven't seen before. So that's a very useful reaction. That should definitely make it into your reaction toolbox. Another reaction, we said that Grignards generally are not useful in reacting with acid chlorides. Better to start with the ester, but there is a way to add a single R group, and that is through what we call a cuprate reagent, and that involves 2 alkyl groups attached to a copper with a lithium counterion, and that in this case will add a single ethyl group to our molecule, taking our acid chloride to a ketone. And so these are both very useful synthetic transformations. Remember that we started with a carboxylic acid to make these carboxylic acid chlorides, and now we have a 2-step sequence that allows us to go from the acid to the aldehyde or the ketone, which can be quite synthetically useful. So I think those are 2 of the more important reactions that we've learned thus far in this chapter. And so once again, we call this organocuprate. And as long as you can make a molecule with a lithium here, you can turn that into a organocuprate. So most straight chain alkanes with a lithium on the end, you can purchase from the chemical company or make yourself in the laboratory. So you can basically put any reasonable R group right here, including branched ones. So this can be a very powerful reagent. We'll see this again, I believe, in the next chapter when we talk about alpha carbon chemistry. I'll again draw your attention to the several figures that are at the end of this chapter. There's a great summary of the acid chloride reactions. I'm not going to redraw that here. You can look at that figure in your textbook.